Okay, so we need to talk about time constants. And so let me write that at the top of the screen here. Let's do this in black. Okay, so we're talking about time constants. And we were a little confused because our differential equations that we had A, B, C, and D, whereas in the model that the scientists put out, there was an R over tau infected here. There was a, let's see, the B value instead of a B, it was, that was equal to R, no, there was no R. That was, let's just cross that out. That was 1 over tau incubated. Okay, that's how long you would be in the exposed category before you became infected. All right, and then there was another C, let's see, so there was a C constant that was for going, let's see, so that was out of B. This was an into I. Oh, and then this was 1 over, yes, T infected, because that was the one, whoops, that went in there. And, oh, and actually there is no D, okay? So we had different constants in our model, and those constants have been changed in the scientific model that was used in the calculator. So we want to understand why. So to understand why, we're going to do a little thought experiment. We're going to pretend that we have a pool of infected people who can recover, and they are isolated from the rest of the world. So anyone who's been exposed or anyone who's still susceptible is being blocked off. So no one can flow into the infected pool. People can only flow out. And in our model, that had been given by a C times I. By the time we had the SEIR model, C times I was what was connecting the two together. So you'll notice C times I is flowing out of I. That's the rate at which infecteds are flowing out and are becoming recovered. So we actually have two differential equations here. So let me write those down. Our equation for infected has simplified to DI dt is equal to C negative C times I. And over here, we can say that dr dt is equal to positive C times I. All right. So now, if we want to find the solutions to these, because they're so simple, we can say di over I is equal to negative C dt. And over here, we can say that dr, oh, this is going to be a little bit tricky. This is, we have to change this to, how can we do this? This is going to be a little bit trickier. Well, let's not worry about that for now. Okay, so I'm just going to erase this because it's going to obscure what we're trying to do. So let me go back to my pen. So we know from what we've done before, this would be ln of I equals negative CT plus a second constant. I'll call that C naught, okay? That constant's going to go away anyway. So if we raise both sides to the, make both sides the exponent of E, this just becomes I, and this became E raised to everything on the left, which we learned became a new constant, which happened to be I naught times E to the negative CT. All right, now this is the important part right here. Okay, C doesn't look anything like T, all right? But if we were to change C to equaling 1 over a time constant, in this case, it would be the time constant T, I, and F, but we're just going to shorten that to 1 over time constant since it's the only one right now. We could rewrite this as I equals I naught times E to the negative T over tau. Okay, that's the Greek letter tau, T-A-U, tau. And so this is going to be more informative, all right, because we could make a little table here. If I write In fact, let me write this as I over I naught equals e to the negative t over tau. Then if I make a little table of t, and I put down here what I divided by I naught. So that's how much I, the proportion of I that's left out of I naught is an E. When this is equal to, when t is 0, e to the 0, so that would make a little, expand this chart one more column or one more row. Let's put t over tau here. And then let's put I over I naught down at the bottom here. So that would mean this is 0, and e to the 0 is 1. Therefore, I over I naught is 1. In other words, we have 100% left because we're at time 0. That makes sense. But when t gets to be one time constant, so tau is our time constant. When t reaches the time constant, then, oh, I should put a negative sign here. Negative t over tau becomes negative 1. And what happens is this has been divided by e one time. And remember, e is about 2.7. When t is equal to 2 tau, so this is what, when I put a double line here, when t is equal to 2 times tau, then this is negative 2. And we've dropped off the amount that we have left in the infected pool by 1 over e squared. And if we keep going, when we get to 3 tau, this is negative 3, and we've dropped off by 1 over e cubed. So when you were working with exponential decay in the past, you probably looked at half-life. It's just easier mathematically if instead of worrying about when something divides in half, we worry about how long it takes to divide by e. So we're dividing by about 2.7 instead of by half. And so the math just becomes easier if we look at how long it takes to decay by a factor of e. And also, instead of doubling times, if this were growth, we would be looking at how long it takes to grow by a factor of e. So this ratio of t to a time constant makes sense because it will be unitless. When you divide a time by a time, you just get a number. So that's convenient. So the scientific model has all of these things over tau. Okay, so now if we go back to the SEIR model, okay, we had some, let's put some, we had the B times IS was right here. This was, I'm sorry, this was A times IS. This was B times E, and this was C times I for the flow right there. And so rather than C, we could rewrite this as 1 over tau INF. Okay, wherever you have an I, we're interested in how fast the I will decay. So we could put this into the equation instead. And that's exactly what you see in the model. Right here, wherever I had BE, this was when people went from being exposed, or when they finished their incubation period, they would switch from E over to I. So this was 1 over tau INC in the model. That's the incubation time times E. So you'll see that showing up in the model. And now here's the interesting part. S, remember, the susceptible population isn't really decaying. Okay, it's being converted over, all right? So what really matters here for A is the infection, how long people are infected, okay? Because the amount of time they stay around being infected will determine the A. So we're gonna have a 1 over tau infected times I because of the I. But then there's this other factor, this R factor, okay? Because while infected, the disease can be multiplied by a factor of R. So it's really it's the infection rate. It's how many people each infected person will infect while they're infected. Okay, so R equals, will be the multiplier of infected people. Now, when R equals something like 2, that's bad, okay? Because for every infected person, they're going to infect 2 more. 1.1 would still be a little bad. Most infected people, that means most infected people would infect 1 other person, but occasionally somebody would infect a little more than that. It still leads to exponential growth. So 1 is the break-even point. That's when they're only infecting 1 other person. So it's just a chain that continues. And if we start removing susceptible people from the population, that actually drives the equations down, even though they could potentially, this is sort of a hypothetical, if they were surrounded by susceptible people. These are the R value is kind of a hypothetical, sort of a best case scenario for the spread of infection. So if we get down to something like 0.9, that's a little good, okay? Sort of good. That will start to cause fewer people to be infected sort of in each generation of the infection. If it was something like 0.1, that would be very good. Oops, very good. Because it would drive the infection rate down very, very quickly. So we have an extra factor of R in the constant in front of the I when we're trying to go from the S to the E. So in this conversion from S to E, there's an extra factor of R that shows up in the equation. Notice that R does not show up in the I to R conversion. The R is no longer there because it's really based on how the I's are interacting with the S's. So we need that R in the equation. So that's a quick explanation of where the sort of scientific constants came from versus what we had used.